Dear friends, welcome to the first episode of my new podcast, The AfterMath. I envision it as a podcast book, a sequel to my book Love and Math, which was published in 2013 and is now available in 19 languages. I see it like an audiobook, but released in installments, with each episode being like a chapter in a book, so they're all connected to each other. Of course, we will also have a visual component, and most importantly, I'm inviting all of you to comment and to ask questions. Your feedback will be very much appreciated. It will make this podcast so much more interactive as it unfolds in real time. So what are we going to talk about? Well, my big passion is mathematics. So naturally, it's going to be a big part of this podcast. Also, since I was a kid, I've been fascinated with quantum physics. And in fact, a lot of my research has been on the interface between math and quantum field theory. So that's naturally another topic of interest. I'm also interested in philosophy, specifically the fundamental questions on the nature of reality. Well, who isn't, right? And also in psychology, specifically Jungian psychology, which I have been studying for the last 10 years through the works of Carl Jung and Marie-Louise von Franz, who was arguably his favorite student. You see, in my mind, all these subjects are deeply connected to each other. And in fact, the main motivation for me to do this podcast is to share my knowledge with you, and in particular to show you how these pieces fit together from my perspective. I will start by talking about some important aspects of mathematics, which are rarely, if ever, discussed these days. One can say that mathematics creates a kind of a bridge between matter and mind. And this provides some very important insights on the nature of reality, but also insights on our lives. So to me, this is not just some abstract stuff that we are discussing just out of curiosity. In fact, they touch upon the most fundamental questions of our lives. Who am I? What is this all about? What is life? What is death? How do we relate to one another? These are the types of questions that I want to talk about. And most importantly, what I will argue is that mathematics shows us that we are all connected to each other, you see. And when I say connected to each other, I mean it at a much deeper level than it is ordinarily understood. Because it's well known today that our bodies are connected to each other through the environment. Duh. Because, the skin is a kind of a membrane through which the inside of the body interacts with the environment. And so through the environment, our bodies are connected. Fine. But what I'm going to talk about is a connection at the level of our minds. Our minds are not isolated from each other. My mind is not locked in my skull. Your mind is not locked in your skull. We are capable of communicating with each other somehow. And mathematics gives us the clearest evidence of this connection, you see. So it kind of becomes a portal to this hidden reality. What is mathematics after all? So to me, it is this vast reservoir of timeless, persistent, and objective knowledge, which is accessible to all of us, even though we don't perceive mathematical objects through our five senses. Think about it. It's a very important point, which is usually missed. And I'm going to explain this in more detail shortly. But roughly speaking, that's because the objects we study in math actually don't exist in physical reality. Let me repeat this. The objects that we study in math, if you look at them more closely, if you examine them more closely, you realize that they do not exist in physical reality. They are not in space and time. You see, where exactly they reside then, if not in space-time, I don't know. It's a big question. It's a big mystery. We'll discuss it. But the first thing to understand is that they are not in physical reality. We do not perceive them through our five senses. And yet, we can talk about it. We can imagine them. We can conjure up these mathematical objects in our minds. And we can talk about them. We can reason about them. And we understand each other. We understand what we're talking about, you see. We can prove theorems about them. We can introduce new mathematical objects, and so on. So it's really fascinating. And I believe that this points us directly to our unity, to our connection to each other. Moreover, the fact that mathematics has been so successful in describing the physics of the universe, as a physicist Eugene Wigner put it, there is this almost unreasonable effectiveness of mathematics in natural sciences. That, to me, points to our unity with nature at a deeper level than is ordinarily understood. And it is this unity between us and nature, that will be one of the main themes of this podcast, the aftermath. Let's get right into it. I want to start by pointing out an important difference between mathematics and physics. Mathematical theorems stay the same. They don't get updated. New theorems get proved, but this does not change the validity of the theorems that were proved before. But our physical theories get updated. For example, Isaac Newton formulated his laws of motion and his theory of gravity. Both were used successfully for more than 200 years. But in the 20th century, both theories were drastically updated. Now, this doesn't mean that Newton's theories were completely discarded. They're still used today because they give us sufficiently good approximate description in many situations. But physicists realize that these theories don't give us a good description in many other situations. Roughly speaking, at high speeds, at small scales, or when the gravitational force is very strong. So, other physical theories were created in the 20th century, which gave us much more accurate description in those cases, namely Einstein's special relativity theory, quantum mechanics, and Einstein's general relativity theory. However, these theories still don't give us a total and complete and precise description in all cases. Quantum mechanics, for example, is incompatible with special relativity. And so it needed an update, which we call quantum field theory. And now we have to reconcile quantum field theory and Einstein's general relativity theory. And we still don't know how to do it to this day. You see, in other words, the best theories that we currently have, quantum field theory and general relativity, are incompatible with each other, and hence they are incomplete. The upshot of this discussion is that physical theories are always approximate. A given theory works well in a certain range of cases, but not in all cases. Physics is always work in progress, you could say. Now, this may sound discouraging to some of us, but I actually think this is not a bug. It's a feature. What it means is that our universe is so incredibly complex that we shouldn't expect any theory to describe it completely. As Richard Feynman put it, the great Richard Feynman, nature's imagination is so much greater than man's. It will never let us relax. It will never let us relax. So now let's contrast that with mathematics. Consider the Pythagoras theorem, which we all study in school. This theorem is about the right triangles. We're talking about the triangle which has one angle is 90 degrees. So then there are three sides. The longer one, which is opposite to the right angle, is called the hypotenuse. And then there are two shorter sides. If we denote their lengths by x and y, and the lengths of the hypotenuse by z, Pythagoras' theorem says that x squared plus y squared equals z squared. Now, this was discovered by Pythagoras and Pythagoreans about 2,500 years ago. In fact, it was also discovered around the same time in other cultures. So that was a theorem proved in those days. And in fact, in Euclidean geometry, it is kind of codified in the framework of a formal system, a kind of axiomatic system that we will talk about in more detail. Now, fast forward 2,500 years. Today, Pythagoras' theorem is still valid. It still expresses the truth about the right triangles. Any right triangle with the sides x, y, z gives rise to this relationship, x squared plus y squared equals z squared. That relation has not changed, nor do we expect it to change in the next 2,500 years. So that's the difference between mathematics and physics that I was talking about. What's even more fascinating is the fact that math and physics actually describe different things, closely connected to each other, but different. And I know this might sound surprising. And in fact, it's very easy to miss this feature. It's one of the most important aspects of the story. So let me explain what I mean. And a good illustration for this difference of math and physics is provided by Euclidean geometry. So Euclid's idea was to establish some fundamental relations between different geometric figures on the plane. Now, what do I mean by a plane? Usually when I teach this in a classroom, so I have a blackboard, say, and I explain to my students, I say, imagine this blackboard extended in all directions to infinity. Okay, but I don't have a blackboard, so let me show you this on my iPad. So here's a page on my iPad, And so imagine extending it in all directions to infinity. Or likewise, you could imagine, a flat tabletop extended to infinity in all directions, or a piece of paper, again, extended in all directions. That's what mathematicians mean by a plane. Already, a first issue appears. What do I mean by saying extended to infinity? Because we don't have this type of infinity available to us in the physical world around us. More on that later, but let's go back to this page. So on this page, I can draw, for example, I can draw a line, or I can draw points. I can have intervals connecting points. I can have circles. I can have triangles, right? And so once I draw this picture, so for example, here is a right triangle that has one of the angles 90 degrees. And let's suppose that I arrange that one of the sides is 3 centimeters and another side is 4 centimeters. And I want to find what the hypotenuse of this triangle is, right? And so here's where I can use the Pythagoras theorem and to say that, well, you have to take the square, 3 squared plus 4 squared. So the result is 9 plus 16, which is 25, which means that the hypotenuse squared is 25. So that is to say that the length of hypotenuse is equal to 5. So it's what's called a 3-4-5 triangle. So it's a triangle in which each of the sides is actually a natural number, and they satisfy the Pythagoras formula. So now, one approach to doing that is to kind of to draw the picture and then to make an accurate measurement. But Euclid's idea was to deal with this kind of once and for all, with this relation for all right triangles, and think of it as a universal relation, and not just do it each time a right triangle appears. So how to do it? So his idea was to start with a certain core principles, which are some statements about these geometric figures that we take for granted, accept without proof. We call them axioms, or sometimes in the past, people use the term postulates, okay? And so then the idea is that you start with a small number of these core principles, of these axioms, and then you try to derive other statements, which we call theorems, from these axioms. And this way, you try to establish some universal relations between the geometric figures, but by pure thought, without any experimentation, you see, without actually going out in the field and measuring things, or drawing them on an iPad or on a piece of paper and measuring things. So this is a brilliant idea, that you're just trying to do it by pure thought, by pure logic, by pure reason. And in fact, what Euclid did was what we now call a formal system. It's the first example of this approach, which has been sort of a bread and butter of modern mathematics, that you produce new statements, new theorems, by starting with a carefully chosen collection of axioms, statements that you take for granted. So, for example, one of the axioms that Euclid used was the following, that if you have 2 points on the plane, there is a unique line which passes through them. Reasonable. And there was a few other axioms of this nature. But the question that I want to ask is, what do we mean by lines, points, circles, and so on? Because you see, whatever I draw on my iPad, or you would draw, say, on a piece of paper, and so on, it's not going to be the same as what is actually considered as a bona fide object in Euclidean geometry. A point in Euclidean geometry is not supposed to have any size. It's not supposed to have any thickness. Likewise, a line is supposed to have 0 width. It has to be infinitely thin, if you will. And it should be completely straight. But in the real world, in the physical world around us, there are no such things. There are no points which have no size. There are no lines which have no width. And perhaps even more importantly, there are no lines which are not wiggly. All the lines in the physical world, they're wiggly. They may look approximately straight from a particular vantage point, but as you zoom in, you will see the wiggliness. The physical world is wiggly. But in Euclidean geometry, we postulate the existence of this absolute, idealized, abstract objects, points, lines, triangles, and so on. And axioms and theorems are about them. Let me repeat this. Axioms and theorems of Euclidean geometry are really about these abstract, pure forms, abstract, idealized geometric figures. They are not, strictly speaking, applicable to the objects that we find around us in the physical reality. So you see, what we learn is that these mathematical geometric figures that we are talking about in Euclidean geometry are not something that we can find, we can observe in the physical world around us. The objects in the physical world are approximate lines, approximate points, approximate triangles, but they're not exactly the objects of Euclidean geometry. Those are idealized, abstract, pure geometric figures which are not, have no place in the physical world. But of course, what we do is a kind of a sleight of hand that we conveniently forget the difference between the two and pretend these are the same objects. But what does it mean, actually? It means that actually, if these are so different, it means that these abstract geometric figures, these points with no size or lines that have no thickness, that are absolutely straight and so on, they actually don't reside in the physical world. So where do they reside? It's kind of clear. They reside in the mental world. They reside in our minds. But what does this imply? The fact that we can talk about them, that you understand perfectly well what I'm talking about. You understand what I'm talking about when I talk about these idealized objects. And it's not like you are perceiving them with your five senses in the physical world. If these objects were present in the physical world, then you look at them and I look at them and they say, okay, we understand each other because we perceive them through our five senses. But as I have explained, that is not the case. And yet nobody has ever told me, when I teach this stuff, Professor, I don't understand what you're talking about. What do you mean by a line without thickness? What do you mean by a point that has no size? Everybody understands that such things exist in our minds. We have the innate capacity to conjure them up in our minds. But then I would argue that our minds must be connected. How else could we talk about them together? How else can we understand each other? How else can we reason about them without having seen them, without having perceived them in the physical world around us, you see? What is perhaps even more shocking is that Euclidean geometry assumes the existence of infinity. Because remember how I talked about the plane as being a page or a blackboard extended to infinity in all directions. Every line on this abstract plane is infinite. It doesn't have a finite length. It doesn't end anywhere, you see. But in our physical universe, there are no such lines. There are no such planes, for the simple reason that the universe is 13.7 billion years old, give or take. And the speed of light is finite, which means that the observed universe, whatever we can observe within our universe, has finite size. It simply doesn't contain infinite lines or infinite planes or any other objects whose of infinite extension, you see. So that shows you even more clearly the difference between the abstract math of Euclidean geometry and the concrete, sort of say, applied math of approximate forms, approximate lines, approximate circles and points and triangles. There is an important feature which is missing in our physical universe, which we have no trouble conjuring up in our minds, and that is lines of infinite length, you see. And in fact, to continue the story of Euclidean geometry, I mentioned that Euclid came up with these axioms and then tried to derive various theorems, such as Pythagoras' theorem, from those axioms. I mentioned one of the axioms, which is about a line passing through two different points. So that axiom does not require you to kind of see the entire line in all of its infinite glory. There are four more postulates that Euclid came up with, and all but the last one, which became known as the fifth postulate, or perhaps now we would say fifth axiom, kind of have this finite nature. So that's something that you could experience just by looking at the finite piece of a plane. But the last one is about parallel lines. The statement is the following, that if you have a line and you have a point outside of this line, I'm drawing this again on my iPad, then the axiom says there will be a line passing through this point which is parallel to the original line. Parallel meaning that it never intersects it. But you see, that means that we're making a statement about these two lines all the way to infinity in both directions. But we have no way of verifying this in our physical world. In our physical world, I can only make approximate renderings of these lines as kind of finite segments of those lines. They will be different from the abstract lines in several aspects. As we discussed, first of all, they will have some thickness, which contradicts the assumption that we make in Euclidean geometry. Second of all, they will not be exactly straight, which we assume to be the case for the abstract mathematical objects in Euclidean geometry. But perhaps what is even more important is that we'll only have access to finite pieces of those lines. But in Euclidean geometry, we are talking about those lines in their entirety as the infinite, as the really genuinely infinite geometric objects. And this fifth axiom, fifth postulate, specifically talks about what happens throughout this line in all the way to infinity. No wonder the mathematicians for the next 2,000 years try to get rid of this axiom, try to prove it from other axioms, because I think intuitively they felt uncomfortable because it was a statement that they were being told to take on faith, so to speak. And that statement dealt with something, with a certain feature of this Euclidean geometry, which is very hard to imagine verifying in the physical world. So you see how interesting. The natural question at this point is, where do these mathematical objects reside? And many mathematicians believe that they reside in what's called the Platonic reality, a kind of a realm of pure forms, which was theorized by the Greek philosopher Plato, who in many ways actually followed in the footsteps of Pythagoras and Pythagoreans. So many mathematicians believe that these abstract forms are real. They do not exist in physical world, as we have just discussed, even in the simplest possible example of Euclidean geometry. So they reside in this sort of mental space that we all have access to somehow, right? So the great logician Kurt Gödel, one of the greatest mathematicians of the 20th century, has said that in his view, mathematical concepts and ideas form an objective reality of their own, which we cannot create or change, but only perceive and describe. Now, I'm not going to try to resolve this question once and for all and argue whether this Platonic realm really exists or not. But the question I'm asking is, how can we possibly understand each other when I talk about points, lines, and triangles? If our minds were separate, I can't imagine how we could possibly understand what we're talking about. And yet, we don't have to make any effort to understand what kind of things we're talking about, you see. And I don't believe it's just because objects of similar kind that approximate them can be found in the physical world. For one thing, no finite interval actually approximates an infinite line. And yet when I say infinite line, I don't think you have a difficulty understanding me. Our mind has the capacity to conjure it up. And what you conjure up in your mind, what I conjure up in my mind, appears to be the same, even though we don't perceive these objects with our five senses. Note one more thing. If we are looking at some object in the physical world and perceive them with five senses, you and I will have slightly different views, slightly different perceptions, because we'll have different angles, different points of view. But with mathematical objects, we all seem to have the same point of view. We don't have different perspectives. How interesting, huh? So this reminds me actually of a very nice quote from Charles Darwin. I'll read it from my book, Love and Math. It's actually in the preface, in the preface to my book. And Charles Darwin, whose work at first did not rely on mathematics, later wrote in his autobiography, "I have deeply regretted that I did not proceed far enough, at least to understand something of the great leading principles of mathematics. For men thus endowed seem to have an extra sense." In other words, he's saying those who understand mathematics have an extra sense. And I would actually say I kind of agree with it, but I would say more. I would say that all of us have this extra sense. All of us have this ability, not just mathematicians. And everybody's a mathematician somehow, even if we don't really notice this capacity that we have. And it's a great gift, I think. It's a great gift that we have to appreciate and celebrate. It shows you the plasticity, the ability of our mind to go much further than we could imagine by being confined just in space and time. So that means that some part of us is beyond space and time. And I think that is an incredibly important consequence or incredibly important conclusion from this discussion. It opens up our horizons to go from feeling as being separate and enclosed and divided and isolated from the rest, from other people, from nature, and so on, to the idea that there is a much deeper connection between us than is ordinarily understood. And what gives us this sense, this evidence for this deep connection, is mathematics. This is what I meant when I said that mathematics is our portal to hidden reality. Well, you could say this example with Euclidean geometry, with points, lines, triangles, and so on, the difference between the idealized, perfect mathematical objects and the objects that we actually find in the physical world around us, it's not that great. You could say that sort of to a naked eye, a slightly wiggly line in space could look like a perfect straight line. So yes, that's correct. But here we're only talking about the most elementary objects of mathematics. As we progress and as we delve deeper into the subject, we find much more refined, much more sophisticated objects. There are all kinds of exotic numerical systems. For instance, the so-called p-adic numbers, which you can Google that. P stands for a prime, and p-adic, A-D-I-C. P-adic numbers, they form a big part of the mathematical universe, but I don't think anyone finds them in the physical world around us. We find real numbers, we find natural numbers, we find rational numbers, and so on, but not p-adic numbers. So where are they in the physical world around us? That's not clear at all. Even with complex numbers has been a big question up until recently. What I'm talking about is numbers like square root of -1, which we usually denote by I. The first mathematician to write about them was an Italian mathematician, Girolamo Cardano, and he was speaking about the mental tortures involved in trying to understand and decipher the meaning of those numbers. These days, they are just bread and butter of mathematics. We don't even think twice about any kind of. There's no mystery about them anymore. And moreover, our best physical theories, the quantum mechanics, quantum field theory, rely on complex numbers. The Hilbert space, which appears in quantum mechanics or in quantum field theory, is a complex vector space. The complex numbers are built, sort of hardwired, are built into it. And so, so you could say, yes, complex numbers in some sense are connected to the physical world, but they're connected in a rather non-trivial way. So this actually shows a very strange way in which some mathematical concepts that initially appear to be purely abstract and esoteric actually then kind of find a back door into the physical world. So maybe p-adic numbers also will somehow, in later theories, will make an appearance, and we will say, okay, well, p-adic numbers actually are integrated into the physical world around us. This hasn't happened yet, and I would say that it's probably safe to assume that most of mathematics will never find its way to the physical world around us. There's no reason to believe that it will. And even those that do, like points and lines and triangles, there is still a subtle but important difference between them, as I explained, you see. So therefore, we have to be careful not to identify our mental world with the physical world. It seems to be that the case that we can actually imagine and conjure up things in our minds which we cannot really observe in the physical world around us. So that's the point I'm trying to make. But you see, if so, then there is a big question about how we can actually talk about this. Because if all of those objects actually did appear in the physical world around us, we would say, okay, yes, our minds could well be disconnected. So here's my mind, here's your mind, but we are both observing the same thing in physical reality. So that's why we can communicate about it. But if we agree that there are some objects in mathematics which we do not find in physical reality, then how can we possibly understand what we're talking about? You see, the same ways that I imagine a straight line, or I imagine periodic numbers, or I imagine complex numbers, or an infinite dimensional Hilbert space, so can you. You may not have thought about it as deeply as I have, but all the information is available, and everybody can learn this. Everybody can understand it. And once you do, we're all on the same page. We can reason about it. We can discuss it. We can exchange ideas about it. We can move to the next frontiers in our research about the subjects, which is how mathematics has been developing, actually, right? So that is a very essential point, that it opens the possibility that our minds are actually connected to each other, because otherwise it looks extremely implausible that we would actually be able to, you would be able to understand what I'm talking about, you see. So I would say that's the biggest takeaway from this discussion, this idea of unity, this idea of non-separation, you see. So we go from this sense of being in a sort of a conflict with each other, in disagreement with each other, being isolated, alienated from each other and from nature. We go from that to this realization of how deeply connected we are. And we're not led to this by some magical thinking, some voodoo. We are led to this by mathematics, the most objective of all sciences, you know? So we have to pay attention to this. And in fact, if you think about it, this has been staring at us this whole time, because we all study Euclidean geometry as kids. But it's just that what I pointed out today are these very subtle aspects of it, which are not usually emphasized. And you see, this is what we're going to do in this podcast. There is a lot more to discuss. In the next episode, I'm planning to talk about non-Euclidean geometry, about how in the 19th century, mathematicians also realized that you can replace this fifth postulate, this axiom of parallel lines that I talked about earlier, with its negation. And this way to come up with much more interesting realizations of geometry, which lead us to this bigger world, the world which is not flat. Just like Earth is not flat, our space-time is not flat. So this idea of non-Euclidean geometry eventually led Bernhard Riemann, the German mathematician, in the 1850s to his theory of Riemannian geometry, which became the cornerstone of Einstein's general relativity theory. And we learned from Einstein, from this theory, that in fact, not only the surface of the Earth is curved, but in fact, our space-time is curved. A ray of light bends around a star, a massive star, something that was confirmed experimentally in 1919 by Eddington, the great astronomer, and his expedition. So there's so much more to talk about, but also, by the way, formal systems. So I have to explain to you the language of mathematics. What is this? What are these axioms? How do they produce new theorems and so on? What happens when we replace one axiom with another and so on? So this is called formal systems. I will explain to you this language. And this will also lead us to another important aspect of mathematics, and that is infinity. We have already talked about it a little bit, but we'll also talk about the infinity of natural numbers, for example. And what does that mean? But let's wrap this up for today. Before I go, I want to tell you something. I'm not by far the only scientist who has suggested this possibility that our minds are connected. And in this respect, I want to talk about Erwin Schrödinger, the great Austrian physicist. The Schrödinger equation is a cornerstone of quantum mechanics. He was an absolutely brilliant man. And, also famous for his cat, the Schrödinger cat. Is he dead or alive? We don't know. I guess one day we'll find out. One day. But he was very interested in these questions, the question of nature of reality, nature of consciousness. And he wrote a book, Mind and Matter. And in this book, he writes about what he calls the paradox of numbers. That is, to him, the appearance of many conscious egos from whose mental experience the one world is concocted. He considered that a paradox of numbers, the seeming appearance of many conscious egos. And the solution to this paradox of numbers, according to him, was the unification of minds or consciousnesses. Their multiplicity is only apparent, he writes. In truth, there is only one mind. In truth, there is only one mind. And he adds also in the book that the empirical fact that consciousness is never experienced in the plural, only in the singular. He says that's the empirical fact. Not only has none of us ever experienced more than one consciousness, there is also no trace of circumstantial evidence of this ever happening anywhere in the world. So you see, he was very much sold on the idea of a unified mind or the unification of our minds. And I also want to mention the interview of a mathematician, Russian-born mathematician, Vladimir Vapnik, who is one of the luminaries in the subject of machine learning. He's a founder of the statistical learning theory and many other important advances in machine learning. So he was interviewed by Lex Friedman on his podcast, and here's what he said. I'm not sure that intelligence is just inside of us. It may also be outside of us. When we prove some difficult theorems, in a couple of years, in several places, people prove the same theorem. In history of science, this happened many times. He gives us an example, the discovery of non-Euclidean geometry, which we'll talk about next time in the second episode of AfterMath of this podcast. And Vladimir Vapnik says there are many examples like this, and I concur. When mathematicians develop something, he said, they are developing something general, which affects everybody. Isn't it what we've discovered today? So maybe, he says, our model that intelligence exists only inside of us is incorrect. It might be that there exists some connection with the world intelligence. The world intelligence. I really like this idea of a world intelligence. Now, interestingly enough, Vladimir Vapnik was saying all this in response to Lex Friedman's question, can machines think? Can machines be intelligent? So, of course, all this stuff is very much connected to the current debate about artificial intelligence, about what these computer systems can and cannot do. And I promise you we will devote a lot of time to discussing this in the subsequent episodes of this podcast. And I will also talk about Jungian psychology, which is very much relevant to all of this. So Jung had this idea of archetypes, which in some ways are close to these Platonic forms, these pure Platonic forms that we talked about earlier when we discussed the question, where do mathematical objects reside? But Jungian idea of archetypes, I think, is more advanced than the idea of Platonic forms. I will explain in what sense. And Carl Jung was actually very much attuned to mathematics. He believed that numbers represent the simplest possible archetypes. He called them archetypes of order. And he actually expected that by looking at mathematical objects such as natural numbers, as well as other mathematical objects, one could actually gain a lot of interesting insights into psychology and into kind of the structure of our psyche, the collective unconscious, and things like that. So we'll definitely talk about all of this, especially in connection with numbers, in connection with infinity, and things like that. But that's all the time we have for this first episode. I'm super excited about this project, as you can tell. And if you enjoyed it, if you like the content, please hit the like button, please subscribe, please share with your friends on social media. And most importantly, please leave comments, leave questions. I'll be happy to respond, to discuss these questions in the future episodes. Also, you can contact me on social media. I'm active on Twitter, on Facebook, on LinkedIn, Instagram, You can see in the description. In the description of this video, you can see my handles on various platforms. I will also put in the description a few links that are relevant or related to the material that we have discussed. And I'm really looking forward to seeing you next time on this new podcast, The Aftermath. Thank you. See you later. Bye-bye.